Today we're going to be looking at two unrelated topics because locks are not really worth a full lecture on their own, but they are related to some of the synchronization issues we were looking at last time, where we used transactions to achieve synchronization between two sessions. And then we'll look at indexes finally, which I've been sort of mentioning all semester. Those are the data structures that allow the database engine to efficiently store and retrieve information. So one final look at this problem where we have lots of clients and a distributed web server and race conditions all over the place. And we saw that the way that we would want to solve this problem is by pushing the synchronization to the common shared point, which is the database. So we would want something like a lock on the database. We didn't use a lock, we used a transaction to solve the problem. But turns out SQL does actually have locks. And transactions are not intended to be used as locks, and they are not locks because other sessions and other transactions can still proceed as long as they aren't interfering with each other. They can solve some of the same problems though. So let's look at locks. SQL has various locking mechanisms. We'll look at table locks and select locks. So as the names kind of imply, a table lock locks an entire table. Kind of like a mutex, except still not a mutex. It's not locking a region of code. It's just providing one session full access to a table. And then select locks where we can only lock the rows that we need to select. So instead of locking the whole table, we can just say select a few rows for locking, or lock a few rows for selecting, and then we can do whatever we need with them. And select locks are tied to a transaction. Table locks are not. So let's see how that works. The syntax for a table lock is just lock table and then the table name and then either the keyword read or write. So we can lock for read or we can lock for write. And we could have multiple lock table statements. So we could lock more than one table and then we unlock all of them with unlock tables. So people commonly confuse locks with transactions. A table lock is not automatically a transaction. So you could lock a table, run a few commands, and then the server could crash, or you could lose your session, for example, and it will not be rolled back. The things that you already did will have taken place. So if you want this to be a transaction, you would also need to use a transaction. So what's the difference between read and write locks? So here's lock table for read. Any session can read from the table, regardless of whether it's locked or not. Other sessions will stall when trying to write to that table, and the locking session will actually fail if it tries to write to that table. So that's a little interesting. The locking session actually kind of has less permission than the other sessions do. Other sessions can try to write and they'll just stall, but the locking session will actually just throw an error if you try to write. And that's just because you have declared that you have locked the table for read only. So why would you ever try to write? And it actually just kind of converts that into an SQL error. Other sessions can also lock for read. So you can have two sessions locking the same table for read. And that's fine. Since it's a read-only lock, it doesn't matter if somebody else is reading. It's just you want to make sure that nothing changes, that nobody can write to it. So that looks kind of like this on the timeline. If session 1 locks some table for read, session 2 can go ahead and select with no problem. Session 1 can go ahead and select with no problem. But as soon as session 2 or any other session tries to do an insert, it will be delayed until the unlock tables from the session that acquired the lock, or until all other sessions have unlocked that table. Okay. Locking a table for write is more restrictive. So the locking session can read and write. So the session that holds the lock can do anything with the table. Other sessions will stall when trying to do anything with the table. So when trying to read or write, they will stall. And other sessions, if they try to lock the table, they will also stall. So this one kind of looks more like a mutex, where if another session tries to acquire the lock, it will stall. If another session tries to do something with the table, it will stall. Although that's an important difference between a mutex, is even if another table doesn't have a lock, it will stall when trying to do anything with this table. So that looks kind of like this. Session 1 can lock a table for write, and then if session 2, even if all it's trying to do is a select, it will be stalled until session 1 unlocks tables. So table locks are kind of like a more blunt tool than a transaction, where you want to lock the entire table, even rows that are not necessarily involved in whatever you're doing. And for that reason, they're actually pretty rare in practice. They're much more heavyweight than a transaction, and they're usually not the right tool for the job. It'd be like using a sledgehammer to drive a nail into a board instead of using like a carpenter's hammer. They lock, like I said, every single row, even if whatever you're doing doesn't involve that row. So when you would use them are if you're doing something like copying an entire table either into or out of a database, and you don't want the table changing while you're doing that. So something like MySQL dump or importing into a MySQL database. So to really illustrate this point that transactions provide finer-grained synchronization than locks do, let's look at this problem we were trying to solve in the last lecture, where if somebody tries to check out a book, it will run the checkout book controller, but we want to leave at least one copy left for the library. So if two concurrent clients tried to check out both of these copies at the same time, we would need one of them to fail so that we leave at least one for the library. And we could use a lock to solve this problem. So we can lock the entire checked out table for write so that nobody else can do anything with it. Figure out how many copies are left available. If there are enough, insert a row into the checked out table, and then unlock tables. And this does solve the problem. It would keep at least one copy for the library, but it's overkill, and it prevents anyone else from doing anything with this table. So even other controllers that don't need to modify checked out but only need to read from it would not be able to run while this controller was running. And there is actually an example of that in the library web server. The all titles controller that produces just this home page, it needs to read from the checked out table in order to produce this column, but it doesn't need to modify the checked out table. So it's read only, so it doesn't need to be synchronized with the checkout book controller, and so it shouldn't be. If there was a race between those two controllers and somebody checked out a book while somebody else was loading this home page at the exact same time, then yeah, there's a race, and you might get a checkout button, or you might get, say, a patron here who has checked out that book, depending on who wins the race. But it doesn't matter. If you get a slightly outdated web page, then if you try to click on the checked out button, even though it's not actually available, then the web server would just say, oh, actually that book's not available. Somebody got to it right before you did. And that's a problem anyway. If you load this page and then go away for 10 minutes and then come back, it's going to be out of date anyway. So you have to be able to handle the fact that clicking on the checked out button may not actually allow you to check out the book if it's out of date. So this controller should not be synchronized with the checkout book controller because it doesn't need to be. And let's see that in action in order to really understand why a transaction is better here. So I have two MySQL sessions running connected to the same database, and in this session on the left, we're going to do modifications to a table, so like simulating the checkout book controller. In this session on the right, we're going to do read only, so like the all titles controller, which only does selects. And we'll use a lock versus a transaction and see how they differ. So first, let's just see what we have here. I have a little table T1 with just 3 rows in it, 1, 2, and 3. So if we're going to do a lock first, so what we do before modifying the table is lock table T1 for write. Okay, now in this other session, If I were to try to select star from T1, I can't, because it's held up. It doesn't fail, it's just stalled until something else happens. So that's because this other session here has completely locked the table. Nobody else can do anything with it. So now this session on the left would proceed and maybe like do its insert into T1 values. Let's add the next row 4. Okay, this other session on the right is still blocked until I unlock tables. Now it can proceed and read all of the rows. Okay, and notice I did not explicitly start any transactions in either of these sessions. Technically, each of these individual commands are run as a transaction by default, but it doesn't matter because I was running them one at a time, so each transaction would completely run and finish before I ever did anything else in either session. So now let's see though if I'm trying to solve this problem with a transaction instead of a lock. So this session over on the left, let's first see what isolation level we're dealing with. So I've already set it to serializable because this session on the left is the one that's running a controller that needs to synchronize with other controllers that might be modifying the table. This session on the right is just in the default isolation level repeatable read because it doesn't need to synchronize. It's read-only, so we can leave it in repeatable read. So now this session on the left, in order to synchronize with other controllers that modify the table, we would need to start a transaction. Okay, and then let's say one of these read-only controllers runs and tries to select star from T1. It can proceed and go ahead and select everything. So this is different from when we tried to do it with a lock. As soon as I locked the table, nobody else could do anything. But now with a transaction, even though I've started a transaction, this other session can read from the table because a transaction is not a lock and it only synchronizes when needed. Even if I had already done some insert over here, so let's insert into T1 a new row, 5, the next row, and then I try to do my select over here. It can go ahead and do it because this session on the right is in a lower isolation level because it doesn't need to synchronize with the other session. Yes, technically I am in the middle of trying to insert a new row over in this session on the left, but the way that the order of operations that happened here is the session on the right just won the race, and it happened to load the web page slightly before the one on the left tried to run the controller, and that's fine. It won the race, so it gets the data that is currently in the table. And finally, the other kind of synchronization we'll look at are select locks. So the way this works is you can lock some certain rows within a transaction. So you just write a normal select statement, and then you add for update on the end to make it a locking select. And the rows that you select, so there may be some where clause here, then those rows are the ones that will be locked. And they're automatically unlocked when the transaction goes out of scope. So when it either commits or rolls back, then they're unlocked. And usually you do want this specifically inside of a transaction. If you do this outside of a transaction, the single select statement will itself be its own transaction, and then it will just immediately be unlocked as soon as the select statement finishes. So that's usually not that useful because usually you want to do something after locking that requires those rows to be locked. So the way this works is, let's say I have this table with 3 rows and I select everything where the value equals 2. So it's going to lock that row and the other ones are free, except I say they are probably free. And the reason for that is it's not technically actually locking rows. The way it works is it's going to lock the underlying data structure that contains those rows. So let's look at this other example here where I'm selecting a range for locking. So I'm locking everything where the value is greater than 1 and less than 5. So in that case, it would look like I should only be locking those 2 rows. And what if I then try to insert a 3? Well, the way the data structure for this table works is that 3 would have to, inserting that 3 would have to modify the part of the data structure that is also holding the 2 and the 4. So this insert of 3 would probably stall in this case, since that part of the data structure is locked. And in fact, it might even stall if I tried to modify this row or delete that row. It might be okay if I tried to modify some row that has a value that's far away, since that row is more likely to be contained in a different part of the data structure. And to make this even worse, this is implementation specific. So our database engine may behave differently than some other SQL database engine in terms of how it implements a select lock. So what, though, assuming that it just locks the rows we want it to lock, what can other sessions do if those rows are locked? They can do non-locking reads, so just a normal select without specifying for update on the end. They will stall on locking reads with conflicting rows, and they will stall on writes with conflicting rows until the session that's holding the lock either commits or rolls back its transaction. So just kind of another little timeline diagram of how this looks with two sessions. Let's say they both start their transaction at the same time, and let's say they both try to run some kind of select for update at the same time. And so one of them will win the race and one of them will acquire the lock. Let's say that the one on the right gets to acquire the lock. It can then go do inserts, it can do other things, and the session on the left is delayed until the session on the right commits. At which point then the other session it will acquire the lock and it can proceed to do its own inserts and then eventually commit. So what's the difference between like this versus serializable isolation level or transactions of various isolation levels? The advantages of a select lock is we don't have to change the isolation level. We can just explicitly lock things that we need to lock. And it gives us fine control over which selects are locked, although with that caveat that we don't actually know how it's going to work based on the different implementations of different database engines. We can't actually guarantee that only the rows we want to be locked will be locked. Disadvantage is, one is that it's not directly supported by LINQ, and the other is that it puts these locking decisions on the developer, so where you have to decide which selects to lock and which rows to lock, whereas if you just think of it in terms of a transaction, the transaction processing system will automatically figure out when and if it needs to synchronize. So we're not really going to look at selecting locks much further because transactions are going to solve pretty much all of the problems that we will have with synchronization.